welcome to CEC lectures. Myself Dr. Priti Jagwani. I am an associate professor from Department of Computer Science, Aryabhat College, University of Delhi. So in this present series of artificial intelligence, in my last lecture we learned about the minimax algorithm, and the today's agenda is about alpha beta pruning. Now, when we say alpha beta pruning, it is kind of a technique which is basically used in adversarial search algorithms. So, let us understand first of all what actually an adversarial search algorithm is. So, adversarial search actually applies to two-player games where each player they are opponents, and each player wants to maximize their own outcomes, and while minimizing the opponents, assuming an kind of an optimal play. And this optimal play here is an assumption. Why I am saying so, I'll tell you in a short while. So this is actually a search technique which is for two players game where each player wants to maximize its own chances or maximize their own outcome while minimizing the opponent's one. So basically adversarial search, when we talk about in terms of artificial intelligence, it is actually a decision making technique which is used in kind of multi-agent environments, as I am saying games. So that game is actually kind of we can say a dual agent environment or something of that sort. So these games are chess, tic-tac-toe. So this AI, adversarial search in AI is a decision making technique which is used in multi-agent environments such as games or strategic simulations, where one agent wants to optimize its move so that the outcome can be maximized while anticipating and countering an opponent's rational and conflicting actions. It uses algorithms like minimax that we have already seen in our previous lecture to navigate the game trees, aiming to maximize the AI's gain while minimizing the opponents. So when we say adversarial search algorithm, there are so many search algorithms which definitely we are going to cover in our upcoming lectures in this course of artificial intelligence paper. So this search algorithm like depth first search, breadth first search and A star can be well suited for single agent environment. So I am sure BFS and DFS are the two very common terms which you people are I am assuming that you people are aware of. So that similar kind of BFS and DFS, that same algorithm is also applied here in case of artificial intelligence, although A star is something which could be new to you guys. So the search algorithm like depth first search, breadth first search and A star can be well suited for single agent environment when there is kind of no direct competitor or there is no conflict between the multiple agents. These algorithms which I am talking about are actually suitable for finding an optimal solution in such scenarios, and these are search algorithms. While if we talk about the minimax algorithm, please try to recall what we have studied in a previous lecture. In minimax algorithm evaluates the alternating max and min moves to choose the best guaranteed action, but it is slow for large game trees. So when the game tree is large, meaning the height of the tree is huge or the branching factor is huge, this minimax algorithm is minimax algorithm becomes very slow. Here comes into the picture today's agenda, which says alpha beta pruning. So alpha beta pruning, when I am talking about pruning is kind of we can say discarding or cutting off some of the branches. So pruning is actually kind of an gardening term. So alpha beta pruning, when we say, it improves the efficiency by skipping the branches that do not affect the final decision. When we talk about the zero sum games where two players compete directly against each other, the adversarial search algorithms like minimax or alpha beta pruning are going to be the most appropriate. So, when we say search algorithm, which are BFS, DFS and A star, these are the algorithms which are to be used in the single agent environment when there is no kind of competition or no competitive environment, while if I am talking about adversarial search, minimax algorithm and the alpha beta pruning are the techniques which comes under this adversarial search algorithms. These are the most appropriate to be used in the scenarios when there are two players competing directly with each other. Because these algorithms like minimax algorithm, which we have already seen, and the alpha beta pruning algorithm can determine the best course of action for each player in these kind of zero sum games. Now, when we say minimax algorithm, and we have seen in detail that how this minimax algorithm works. So, please recall that minimax algorithm is actually a backtracking algorithm in which we backtrack starting from or we can say starting from the bottommost branches or the leaves, we can say. And this backtracking algorithm recursively tries different possibilities, and it also backtracks along when the solution is not found. So, in the context of minimax algorithm, this involves exploring all the possible moves in the game tree that evaluate each potential outcome and making decisions based on the evaluation. So, this is what your minimax algorithm is. So, basically it is kind of used in decision making trees. It recursively tries to find out the possibilities, kind of it is an backtracking algorithm. And the diagram, if we look into try to look a diagram of a tree which uses minimax algorithm, here is one. This is, I can say, one of the most simplest tree which is using minimax algorithm. Why I am saying it is simplest? Because it is not having too many branches, neither too much of depth is there. So, the first ply is max, the second ply is min, and the leaf nodes are having their utility scores, what we call. Here we have 2, 5, 1 and 9. So, when we try to minimize the possibilities at the middle layer, minimum number of 2 and 5 is 2 will be kind of we can say taken up to that particular level. Minimum of 1 and 9 is going to be 1 taken to the middle layer, and at the top layer, which is going to find out the maximum of the two numbers which are at the minimum min layer or min ply, which are 2 and 1. So, the max is going to be 2. So, in this way your minimax algorithm works. So, this diagram was actually representing a binary tree that holds the possible game states and moves in a game, we can say, with each leaf node representing a final game state, and this was kind of we can say our minimax tree. So, fine, but here again please notice that this is one of the, I can say, simplest version of a minimax tree, which is not having which is neither having too much of depth nor too many branches. But still, if we deal into the time and space complexity of the minimax algorithm, we need to see that your minimax algorithm explores the complete game tree using a depth first search approach, and that we have already seen. Now, using this depth first search approach, it considers all possible moves at each level. So, the time complexity of the minimax algorithm can be written as order of b to the power m. Now, what is this b and m here? Where b denotes the legal moves available at each point and m denotes the maximum depth of the tree. So, number of kind of we can say legal moves to the power of the maximum depth of the tree. So, now please imagine if your maximum depth of the tree is large and number of legal moves in terms of, I can say, branches is more, your complexity is going to kind of in a way I can say explode. So, definitely this minimax algorithm is going to be very slow in case of with reference to, I can say, large trees. Now, this complexity basically arises because at each level of the tree, the minimax algorithm must consider all the B legal moves, because if there is a move which is legal, it has to be considered by minimax algorithm. And this process repeats recursively for all the M levels until a terminal state is reached. So, the complexity is too much. So, this was actually about time complexity. So, if we talk about the space complexity, so the space complexity of minimax algorithm actually relies on two things. One is how the algorithm generates the action and how the algorithm stores the actions. So, in the case where if all the possible actions are generated and stored simultaneously, the space complexity can be written as order of B multiplied by M, where again B denotes the legal moves available at each point and M denotes the maximum depth of the tree. So, the time complexity was order of B to the power M, while your space complexity is order of B multiplied by M or order Bm. So, this is about the time and space complexity of minimax algorithm. Fine, we have also seen the minimax algorithm, we have looked into the kind of time and space complexity of this thing. But now what happens when we say there are so many branches and depth is too much. So, here comes into the picture which is alpha beta pruning, which is kind of an optimization technique that significantly improves the efficiency of minimax. So, there is kind of an adversarial search, minimax algorithm is there within that category, and alpha beta pruning, we can say it is kind of an optimization technique which improves the efficiency of minimax. How it improves the efficiency of minimax algorithm, let us see. So, it removes, or we can say it prunes the branches, and hence the name alpha beta pruning. It removes the branches that cannot possibly affect the final decision, avoiding unnecessary computation. So, all the B possibilities are not needed to be considered at all the kind of M levels, I can say. Whatever, there are some branches which are not going to kind of affect the final outcome, those branches are need not to be kind of we can say evaluated or calculated, they can be pruned. So, pruning here means kind of cutting down branches and leaves, as I was talking about. In artificial intelligence, this alpha beta pruning, if we say, is actually the pruning of useless branches in decision tree. So, whatever decision tree you are having, if it is having too much of depth and the branching factor, you need to prune the useless branches. Now, this alpha beta pruning algorithm was discovered independently, not kind of in the context of artificial intelligence specifically, by researchers in 1900s. More specifically, what we can say about this alpha beta pruning, it is a search optimization technique that improves the performance of the minimax algorithm. Minimax algorithm basically a decision making process which is commonly used in two players zero sum game like chess, and in such games when one players aim to maximize their score, other will definitely kind of seeks to maximize it. Now, operation of minimax algorithm is in the form of represented in the form of a tree structure, where all the possible game states are being explored recursively, and leaf nodes are being assigned values on the potential outcomes of the game, and this minimax algorithm propagate these values up the tree to the final optimal move. Now, when the complexity of the game increases, the number of possible states grow exponentially, leading to a very high computational cost. As we have seen, the time complexity is B to the power M, while the space complexity is B multiplied by M, and that is where your alpha beta pruning becomes kind of very crucial, because it prunes the branches that cannot influence or they are not going to influence the final decision. It also reduces the number of nodes the minimax algorithm needs to evaluate, because most of the branches, or I can say at least some of the branches are kind of going to be pruned. So, by this pruning or by eliminating the unnecessary computation, this alpha beta pruning actually simplifies the decision making process, enabling faster and more efficient evaluation. So, that is what the advantage of alpha beta pruning is. As a result, we can say alpha beta pruning is practical for so many real time applications, such as artificial intelligence applications like game playing or game playing AI, where the crucial or the critical components are speed and efficiency, because both are going to be kind of improved when we talk about the alpha beta pruning. Now, let us try to understand what this pruning is, how it is done. That definitely we are going to look into, but what actually this alpha beta pruning is, that we need to kind of understand with the help of a Minimax game tree. Now, here is a Minimax game tree which definitely we are going to kind of explore. So, you can see at all the nodes except this the leaf nodes, there are some values written which are in the form of alpha and beta. We will definitely talk about what actually this alpha and beta is, and the kind of name of the plies are given, which is the max ply, min ply, max ply, and the final terminal nodes are there. And please kind of please notice that at the branch E, or at the right child of the node E, we have put in a kind of a cross. So, basically that branch is going to be pruned, and how are we going to select that which are the branches to be pruned? That is how this actually works, and definitely yes, we need to look into what actually your alpha is and what is beta, and how are we going to work out with this your alpha beta pruning method. So, that image which we have just seen was actually of a Minimax game tree combined with alpha beta pruning, where max and min levels, as we have seen, evaluate the child nodes to compute the optimal value, and the branches, for example the right branch of the node E is actually pruned in this alpha beta pruning, or in this tree with the help of alpha beta pruning, because finally kind of or we can say we have reached on to a conclusion by working of this alpha beta pruning, that this branch which is on the right of the E is not going to affect the final outcome, and because of this pruning, unnecessary exploration, unnecessary computation is being kind of we can say reduced. Pruning, as I have already told you, cutting off the branches in the search tree, that cannot influence the final outcome, and hence it saves time and computation. Now, when we talk about this alpha beta pruning as an optimization technique in the Minimax algorithm, so we need to understand that what actually this alpha is and what actually this beta is. So, during the Minimax traversal, there are two values which are maintained. So, actually we can say the three values. One is the value of the node, another value is the alpha, and the next one is the alpha and beta. So, alpha and beta values we need to kind of we can say maintain. So, what actually this alpha is? Alpha is the best score the maximizer can guarantee so far, while your beta is the best score the minimizer can guarantee so far. Alpha, when we talk about, it represents the best or highest value for the maximizing player, which the maximizing player can guarantee so far, and it acts as a lower bound. Now, please listen very carefully. It represents the best value that the maximizing player, or I can say the AI agent, can guarantee so far, and it acts as a lower bound. Initial value, because it acts as a lower bound, the initial value of alpha is minus infinity, and that value starting from kind of the root node is going to percolate to the leaf nodes, update it over there, and then kind of the new value is being given to the nodes above. Obviously, in the kind of in a backtrack fashion or backtrack search manner. initial value of alpha is minus infinity. When we say beta, as I have told you, the best score minimizer can guarantee so far. It represents the best or the lowest value that the minimizing player, which is actually the opponent of the AI agent, I can say, can guarantee so far. It acts as an upper bound, and the initial value of the alpha is plus infinity. So, the initial value of the alpha is minus infinity, initial value of the beta is plus infinity. So, for beta it is plus, and for alpha it is minus. Now, when we say pruning condition, so when your alpha is greater than equals to beta, the branch is cut off because it is not going to affect the final decision. So, now we need to maintain the value of the node, which is obviously in the form of the utility score, kind of residing at the leaf nodes. We also need to maintain alpha value, we also need to maintain the beta value. Now, how are we going to work with these alpha and beta values? So, the first step comes as the initialization. So, we need to set up the initial values where alpha is minus infinity, beta is plus infinity, and these two values together what these values are going to represent. So, these represents the worst possible score for the maximizer and the minimizer both, and we need to kind of we can say pull these scores up, or we need to optimize these scores. So, the initialization is going to be the first step where we are going to set the initial value where alpha is equals to minus infinity, beta is equals to plus infinity. These are the worst possible scores for maximizer and minimizer. Now, in the next step, when we talk about the max node evaluation for each child of a max node, recursively evaluate using minimax algorithm or the minimax search. With alpha beta pruning, we need to update the alpha. Now, alpha is going to be the maximum of alpha or the value. If alpha is greater than equals to beta, we need to stop evaluating the remaining children. That means kind of we can say we are cutting off a beta, or here what we call is the beta cutoff. Now, step 3 is, so this was the max node evaluation which comes after the initialization, which this was the max node evaluation which comes after the initialization. After this max node evaluation, the next steps comes as the min node evaluation. For each child of a min node, we need to recursively evaluate using obviously this minimax with alpha beta pruning. We need to update the score beta, which is beta is equals to min of beta or the value. Now, what is this value? That we are going to definitely talk about when we look into the working procedure. And if beta is less than equals to alpha, we need to stop evaluating the remaining children, and this situation is known as alpha cutoff. So, we have 3 steps. One is the initialization, in which we are saying we need to set up the initial values, alpha as minus infinity, beta as plus infinity. Then there comes the next step which says max node evaluation, where each child of the max node is evaluated recursively using minimax and alpha beta pruning. Alpha is being updated when we are kind of evaluating the max nodes, and alpha is going to be the value maximum value of the two. One is the alpha and another one is the value. Now, value we are definitely going to talk about. When alpha is greater than equals to beta, we stop evaluating the remaining children, and this scenario is known as beta cutoff. While at the third step, which is the min node evaluation, for each child of the min node recursively we need to evaluate this using minimax and alpha beta. We need to update the beta as the minimum of the values of beta and the value. Now, if your beta is less than equals to alpha, we will stop evaluating remaining children, and this scenario is known as alpha cutoff. Now, if we kind of look into one of the examples of alpha beta pruning, let us take this example at first. So, here you can see there is a kind of a simple tree, although it is not as having the branching factor more than what we have seen in this lecture in terms of minimax, but this is also kind of a simple tree, I can say. So, here different plies are given. So, we have max ply, then we have min ply, then again the max ply, and then finally we have some terminal nodes. So, A is at the max ply, min ply is having B and C nodes, while D, E, F, G are at again max ply, and the terminal nodes are having some of these cores. And this is a simple tree if we want to evaluate the optimal moves using the minimax algorithm. Now, but the agenda here is not the minimax algorithm, but we need to look into how this alpha beta pruning is going to help us in order to cut short the branches which are not going to affect the final outcome. And initially if we are going to work on it, we will kind of set up the initial values of alpha as minus infinity and beta as plus infinity initially, and then we will kind of move on to the next steps of max node evaluation and min node evaluation. In this lecture, what we have looked into, what actually the alpha beta pruning is, where it kind of stands, and we also looked into what actually adversarial search is, and how this alpha beta pruning is, why we need this alpha beta pruning, that we also kind of looked into. And apart from that, we have also seen that kind of the 3 working steps of alpha beta pruning, although we have not seen it with the help of an example. That is going to be covered in the upcoming lecture. Here is a list of references which is being used for the preparation of lecture. I hope you have enjoyed this one. I will see you in the next one with the example of alpha beta pruning. Till then, take care. Goodbye.